Introduction. The LRU replacement policy and its approximation have remained as the de facto standard for replacement policy in on-chip caches over the last several decades. While the LRU policy has the advantage of good performance for high locality workloads, it can have a pathological behavior for memory intensive workloads that have a working set greater than the available cache size. There have been numerous proposals to improve the performance of LRU. However, many of these proposals incur a huge storage overhead, significant changes to the existing design, and poor performance for LRU friendly workloads. Every added structure and change to the existing design requires design effort, verification effort, and testing effort. Therefore, it is desirable that changes to the conventional replacement policy require minimal changes to existing design, require no additional hardware structures, and perform well for a wide variety of applications. This paper focuses on the designing a cache replacement policy that performs well for both LRU friendly and LRU averse workloads where while requiring negligible hardware overhead and changes. We divide the problem of cache replacement into two parts: victim selection policy and insertion policy. The victim selection policy decides which line gets evicted for storing an incoming line, whereas the insertion policy decides in where in the replacement list the incoming line is placed. For example, the traditional LRU replacement policy inserts the incoming line in the MRU position, thus using policy of MRU insertion. Inserting the line in the MRU position gives the line a chance to obtain a hit while it traverses all the way from the MRU position to the LRU position. While this may be good strategy for workloads those whose working set is smaller than the available cache size or for workloads that have high temporal locality, such an insertion policy causes thrashing for memory intensive workloads that have a working set greater than the available cache size. We show that with the traditional LRU policy, more than 60% of the lines installed in the L2 cache remain unused between insertion and eviction. Thus, most of the inserted lines occupy cache space without ever contributing to cache hits. When the working set is larger than the available cache size, cache performance can be improved by retaining some fraction of the working set long enough that at least that fraction of the working set contributes to cache hits. However, the traditional LRU policy offers no protection for retaining the cache lines longer than the cache capacity. We show that simple changes to the insertion policy can significantly improve cache performance for memory-intensive workloads while requiring negligible hardware overhead. We propose the LRU insertion policy (LIP), which places all incoming lines in the LRU position. These lines are promoted from the LRU position to the MRU position only if they get referenced while in the LRU position. Lip prevents thrashing for workloads whose working set is greater than the cache size and obtains near optimal hit rates for workloads that have a cyclic access pattern. Lip can easily be implemented by avoiding the recency update at insertion. Lip may retain the lines in the non-LRU position of the recency stack even if they cease to contribute to cache hits. Since LIP does not have an aging mechanism, it may not respond to changes in the working set of a given application. We propose the bimodal insertion policy, BIP, which is similar to LIP except that the BIP infrequently, with a low probability, places the incoming line in the MRU position. We show that the BIP adapts to changes in the working set while retaining the thrashing protection of lip. For LRU-friendly workloads that favor the traditional policy of MRU insertion, the changes to the insertion policy are determinantal to cache performance. We propose a dynamic insertion policy DIP to choose between the traditional LRU policy and the BIP depending on which policy incurs fewer misses. DIP requires runtime estimates of misses incurred by each of the competing policies. To implement DIP without requiring significant hardware overhead, we propose set dueling. The set dueling mechanism dedicates a few sets of cache to each of the two competing policies and uses the policy that perform better on the dedicated sets for the remaining follower sets. We analyze both analytical as well as empirical bounds for the number of dedicated sets and show that as few as 32 to 64 dedicated sets are sufficient for set dueling to choose the best policy. An implementation of DIP using set dueling requires no extra storage other than a single saturating counter and performs similar to LRU for LRU friendly workloads. Insertion policies come into effect only during cache misses. Therefore, changes to the insertion policy do not affect the access time of the cache. The proposed changes to insertion policy are particularly attractive as they do not require any changes to the structure of an existing cache design, incur only a negligible amount of logic circuitry, and have a storage overhead of less than 2 bytes. Our evaluations with 16 memory intensive benchmarks show that DIP reduces the average misses per 1000 instructions (MPKI) for a 1 MB 16-way LRU managed L2 cache by 21.3%, bridging two-thirds of the gap between LRU and Biledy's optimal replacement (OPT).